Our next job is to look at Newton's second law in rotational reference frames. But before we can look at that, we have to take a step back and discuss a few items of rotational kinematics, which is rather non-obvious and needs its own discussion. A good place to start, I think, is with Eulers' rotation theorem. It says that any displacement of a rigid body that leaves one point on the body fixed is a rotation about some axis through the fixed point. In other words, if you take some object and handle it and place it in such a way that at least one point of the body didn't move, then whatever you did to it can be described as a rotation around some axis through that point. That is surprisingly involved to actually prove, so I'm not going to do that here, but it is pretty intuitive. It has important consequences for mechanics. In particular, it means that we can take the general motion of any rigid body and decompose it. We can say that it consists of a translation around the center of mass, or a translation of the center of mass, followed by a rotation about the center of mass. The way you can see that is pretty easy. Let's say we have some rigid object like this, and then it undergoes some motion. Well, we can always say, let's say that we have some translation that maps the old center of mass onto the new center of mass. To whatever extent that doesn't make the body overlap with itself, well, you can fix that with some rotation. So that means that, let me fix this so that they really are overlapping. So you already know that translation of the center of mass is something that we can take into account relatively easily. We just have to look at the sum of all the forces acting on an object, so we can treat that as a separate thing, which means that then the rotation of a rigid object becomes something that can also be treated separately, and that's one reason why rotation is so important. Here, though, we are interested in a couple of other results. Now, rotation, as it says here, is about a fixed axis. It's about an axis. So that means that we can treat it as something that consists of an angle and that axis. In other words, we have some magnitude and we have some direction that's given by the axis. So we then have a natural vector description of rotation. So we can take the vector theta, for instance. That's going to be the magnitude theta times u hat, and u hat is now the unit vector in the direction of the axis. So this specifies angular position. And we could, of course, take the time derivative. And then we get angular velocity. you take two time derivatives, well, then we get angular acceleration. So we should also note here that I have not used the same u hat for all three cases. We have u hat prime, u hat double prime. It doesn't mean that the derivatives of one another, it just means that there's no reason a priori why the vector theta, omega, and alpha should be in the same direction. They can be pointing in very different directions, just as the position vector, velocity vector, and acceleration vector, linear acceleration vector, can be, for a given object, can point in completely different directions as well. To figure out the sign convention here, we use the right-hand rule. So if this is omega there, let's say, then we can take the right-hand fingers and take it in the direction of rotation, and then the thumb will point in the direction of the corresponding vector. So u hat, if you look head-on from u hat, then the rotation looks counterclockwise. Now, what we're interested in doing here is to look at different frames that are rotating with respect to one another. So we use two frames. We're going to call them S0. That is the inertial non-rotating frame. And then we have the S frame, which is rotating but fixed in the object. So just to pick an example here, we can look at the Earth, right? The Earth is rotating. So it is not an inertial frame. We can describe what's happening on the Earth using this S0 frame here, which consists of the vectors of the coordinate system given by x0, y0, and z0. But that's not always very convenient, because the coordinates then keep changing for a given location on Earth. It'll be much easier to work in this red S frame, x, y, and z, because then a given location here will, like Blacksburg, will always have the same coordinates in the rotating frame. But it is unfortunately non-inertial, and we need to find a way to deal with that. So just to be completely clear what we mean, the red reference frame here rotates with the object, just like the arrows do here. The black reference frame is stationary and does not rotate with the object. Now, I could work with the picture of the planet Earth here, but that would be a little complicated. So we'll stick to something a little simpler. And that will be a rotating disc, like this. So here is a rotating disc. It is rotating with angular velocity omega, like this, and this is occurring around the z-axis. So there's a z hat. We're going to pick a point here on the rim. I'm going to call it P, and the position vector of that point is R. Move this to the side here. Now, one important thing that is to some extent at the root of the difficulties of working with rotational kinematics is the fact that if we look at the vector r, seen as a vector, it is the same in both S and S naught, both in the rotating and the non-rotating reference frames. But its components are not the same, and its time derivatives are not the same. Let's see what I mean by that. If you look in S, okay, that is the reference frame that rotates with the body. Now, P is a point on the body, so that means that R is fixed in the rotating frame. So if I then take dr dt as seen from the S frame, the rotating frame, that's going to be 0. If we look in the S naught frame, we have some velocity here, the r dt S naught, and that's not 0, right? Because now r is going to be rotating around the z-axis. So even though r as a vector is the same, the time derivatives are going to be different. Now, if we're interested here in this vector v, we can see that that's going to be pointing along the direction of the rim here, like that. This is the vector v. Let's just make it black. I'm also going to be needing this distance here, the perpendicular distance from the point P, or from the axis of rotation and the point P. And that is what we usually call rho. It means that we have a rho hat in this direction. Okay? Now if you want to calculate what this velocity is equal to, we can see that it's going to be in the direction here along the rim, so that's the phi hat direction in cylindrical coordinates. Its magnitude is going to be the velocity at this point, that's going to be rho times omega. So this is equal to rho omega phi hat. Okay. Now this distance rho here, if we call this angle here theta, that's r sine theta, and that multiplies rho and phi hat. And phi hat here, we can write that as the cross product of z hat with rho hat. Hopefully you could see that. That's true for any coordinate system that's orthogonal. You can find one unit vector by taking the cross product of the other two. And the only thing that you have to make sure of is you get the sign right. So working in cylindrical coordinates, that has to be correct. Right. So we can plug that in here, and we can group things a little bit differently, so that we get like that. Now another thing that we can rotate for r is that rho is along its perpendicular component to the axis. It will also have some longitudinal component along the axis of rotation. So we could write that r is some r perpendicular plus some r parallel. And the perpendicular component here is going to be what? R sine theta. And that's in the rho hat direction. And then it's r cosine theta, and that's in the z hat direction. Now if I take r cross z, or r cross z hat, can see that this term has to equal to 0 because it will actually essentially be z cross z. So we can write this term here as r perpendicular. So we have therefore equal to, and this of course now is omega, right, the vector omega. So this is omega cross r perpendicular, but omega is along z hat. So this is the same now as omega cross r. Just the parallel component will not figure in the cross product. In other words, we will get that the velocity, and that's the velocity seen in the non-inertial reference frame, that's important to note, is the angular velocity vector omega cross the position vector r. And that's the main result from this video. In the next video we're going to generalize this and then use it to derive an addition formula for angular velocity.